Welcome. This video is going to introduce you to Hess's Law. Sometimes measuring the enthalpy change for a reaction is going to be really difficult, if not impossible. And this is because some reactions occur extremely slowly, like the formation of diamonds, or sometimes the conditions are hard or dangerous to duplicate in the lab. Whatever the reason, Hess proved that if you can find and add two or more thermochemical equations to produce the final equation you're interested in, then the sum of the enthalpy changes for those equations is going to be equal to the enthalpy change for the desired reaction. So here's an example. Trying to produce sulfur trioxide in the lab usually produces mostly sulfur dioxide, so you don't really get an accurate enthalpy change for that, not for SO3. So instead, you can calculate the heat of formation for sulfur trioxide by using the two equations I've listed here. Sulfur plus oxygen produces sulfur dioxide, whereas sulfur trioxide decomposes into sulfur dioxide plus oxygen. So the equation we're interested in is the formation of SO3, which is shown with the balanced equation 2 sulfur plus 3 oxygen yields 2 sulfur trioxide. And you notice I've included the state equations because that's important that you're referring to the same state as you add these equations. So I need to look at the two equations I've been given and decide if each of those equations contain the reactant or product I'm interested in, and if that equation has got it on the correct side, it's going the correct direction, and if it has the correct amount. So let's look at these two equations more carefully. I've got my desired equation at the top. So if I look at the first equation, sulfur plus oxygen equals sulfur dioxide, I see that both sulfur and oxygen are reactants I need. Sulfur dioxide isn't something I need, but that will take care of itself, hopefully. And the sulfur and oxygen are on the correct side that I want. They're on the reactant side, but they aren't in the correct amount, so I'm going to have to deal with that. The second equation, 2SO3 decomposes into 2SO2 plus O2. In this case, I have my product, but it's on the wrong side, but it is in the correct amount. So I'm going to have to make an adjustment to each equation. I'm going to double equation 1, even though that's not going to give me quite enough oxygen. Again, these things have a way of working themselves out because I notice my second equation also contains oxygen. And so then that means I'm going to have to double this as well, double the enthalpy. And then the second equation, I'm going to go ahead and flip this running the opposite direction, so this is going to become a negative value. So let's look at this slide where I've summarized the changes I've made. I've doubled the first equation, I flipped the second equation, and I've also shown the change, the corresponding change to the enthalpy value. Then I can go ahead and add these two equations up. I end up with 2S plus 2O2 plus 2SO2 plus another O2. And on the product side, I have 2SO2 and 2SO3. My enthalpy values then are negative 297 times 2 plus a negative 198. So then when I look for common factors on each side of the equation here, I see that the SO2 cancels out, and the O2 and 2O2 can be added together, and I have the desired equation of 2S plus 3O2 yields 2SO3. And my enthalpy change is negative 792 kilojoules. So I like to think of Hess's law as the flippy-switchy law, or if you flip, you must switch. Okay, meaning if you flip the equation, you need to switch the sign, but that also extends to anything else you do. If you double the equation, then double the enthalpy. So here's an example for you to try. Determine the enthalpy change for decomposition of hydrogen peroxide into water and oxygen gas using the following equations. So I'd encourage you to pause and see if you can do this. You'll need to start by writing the equation, the desired equation, and then evaluating the two equations you've been given. So my desired equation is going to be H2O2, which is a liquid, and it's going to decompose into H2O liquids, since it says water and not water vapor, and oxygen gas. So to balance this then, I've got 3 oxygen on this side, so I'm going to need a 2 here and a 2 here to have a balanced equation. So if I look at equation 1, H2 plus O2, that includes one of the products, and then H2O liquid, this includes the product. So even though O2 is going to be needed on the product side, I apparently need to leave this equation in the direction it's written. It's also in the amount we want because each equation is showing a product of 2 H2O, 2 moles of water. So my second equation is going to have to help me out with the oxygen and the peroxide. And if I look at it, it does have the peroxide, it does have the oxygen, but it's running in the reverse direction, and I need to double it. So I'm going to have to flip this over to H2O2, gives me H2 plus O2, which means I'm going to flip my sign to a positive 188, and I'm also going to have to double this to 2, 2, and 2, which means I'll have to double this. And now when I combine that with my first equation, 2H2 plus O2 yields 2H2O. And I'm not putting the state signs in, even though those are important. But we've already checked that they match up, so I'm not going to be too concerned about those. And then this remains negative 572. So when I add this up, I have 2H2O2 plus 2H2 plus O2 yields 2H2 plus 2O2 plus 2H2O. And then my delta H is going to be 2 times 188 plus a negative 572. And when I look for my common factors on each side, I've got 102 here, which will reduce this to 102 on this side. I have 2H2 on both the left and the right. So now when I evaluate this, it appears I've duplicated the equation I'm interested in. 2H2O2 yields 2H2O plus 1O2. So I'm going to scroll this up one more time and write my final equation. 2H2O2 liquid decomposes into 2H2O liquid and O2 gas. And when I go ahead and calculate the delta H, I find a delta H equal to negative 196 kilojoules.